Hi everybody, this is Dr. Nigro with a Physics Fundamentals screencast looking at elastic collisions. I'm also going to include in here and inelastic collisions. All right, in the last screencast we talked about total inelastic collisions where the two objects are apart, initially collide and then move as one after. All right, if it's not a total inelastic collision, if it's just an inelastic collision, then that is not going to be the case. So that's why I'm going to group inelastic collisions in here with elastic collisions. But we will talk about there is a very specific difference between an elastic collision and an inelastic collisions. Both of them fall under this hit and bounce idea, whereas a total inelastic collision hits and sticks. Here they're going to run into each other, but the two objects are going to continue to move separately after the collision. All right. If we are looking specifically at elastic collisions, here momentum is conserved, which we expect, but also energy. So momentum and kinetic energy are conserved if it's an elastic collision. And this is something that is very difficult to do. When two objects collide, it is very hard to conserve energy because generally speaking, you get sound or things get deformed and heat is produced. So energy gets transformed as part of the collision. But for something to be elastic, the energy also must be conserved. All right, so this is only seen for gas particles. Matter of fact, it's a tenet of the kinetic molecular theory, and other small particles that may come into contact, such as subatomic particles. All right, the closest that we get for what we can visualize would be billiard balls or pool balls. So billiard balls are close. All right, but even they aren't perfect because you can hear it. When they hit each other, you get a click, and that click means they have lost some of the energy, but it's pretty close. All right, if we were to look at the plot of a purely elastic collision, velocity and time, all right, we would have one object, let's say it's moving at 2 meters per second, and then we would have a second object moving towards it, let's say at negative 2 meters per second. When the collision happens, all right, then that object that was moving to the left is now moving to the right at the exact same speed. And then the same thing happens for my first object. Now it's moving in the opposite direction at 2 meters per second. All right, but you can see if I were to calculate the kinetic energy before and then calculate the kinetic energy after, the kinetic energy before would equal the kinetic energy after. And that is one of the rules for it to be considered elastic. All right. At the same token, the relative velocity before compared to the relative velocity after is also going to be the same. All right. So the relative velocity before will equal the relative velocity after. All right. So if we have that situation, then we are going to have an elastic collision. All right. Now, what would be the formula? What does the formula look like for an elastic collision? Well, you can see the two objects are separate before and they are separate after. So that flows right into our conservation of momentum, right? Where the mass of cart A times its velocity plus the mass of cart B times its velocity must equal the mass of cart A times its velocity after plus the mass of cart B times its velocity after. So this is what an elastic collision's conservation of momentum formula looks like. All right. Now, that can be rearranged into a second formula, which can be handy. All right, I'm not going to do the actual rearrangement here, all right, but we could look at it in terms of the mass of A. So if I isolate the mass of A from this formula, I end up with mass of A times the velocity of A minus the final velocity of A. And that's going to be equal to the mass of B times the final velocity of B minus the initial velocity of B. All right, and this formula can be handy, right? It's not as complicated as the earlier one. So, I mean, you're welcome to use that formula as well. All right. Now, because the kinetic energy is also conserved for an elastic collision, I could set up this whole formula that looks at the kinetic energy before and set it equal to the kinetic energy after. I can do all this rearrangement, and then what I do is a substitution between that formula and this one that I just wrote, and you end up with this formula that looks like the velocity of A plus the final velocity of A must be equal to the velocity of B plus the final velocity of B. All right, now this only works for elastic collisions, and that only happens because the kinetic energy before is equal to the kinetic energy after. If it's not an elastic collision, you cannot use this second formula. This one you can use. This one's okay. All right, but this second formula only for elastic collisions. All right, so what if it's not elastic? What if we don't conserve energy? Momentum's conserved, but energy isn't, and the two objects are moving separately before and after. What is that? Well, that is an inelastic collision. It's not a total inelastic collision, but it's elastic. And it happens when kinetic energy is not conserved, but objects remain separate. All right, so we're still going to have this formula when we talk about the conservation of momentum. All right, but our plot is going to look a little bit different. All right, so if we draw out our velocity versus time plot again, all right, I'm going to keep 2 meters per second and then negative 2 meters per second. But because this collision is not elastic, I'm not going to really conserve that energy. So maybe now it's moving at 1 meter per second in the positive direction, whereas my initial cart, maybe it's moving at negative 1 meter per second. All right, so you can see, just like we saw before, all right, we're going to have a certain kinetic energy value here, and then we'll have a second kinetic energy value here. All right, and the kinetic energy value initially is going to be greater, the kinetic energy value final, which means that we have not conserved that kinetic energy. Same thing, the relative velocity initially versus the relative velocity final are also not going to be equal. So the relative velocity initial, again, will be greater than the relative velocity final. All right, so we still have two objects. They collide and they remain separate, but we don't conserve energy. We do conserve momentum, but we don't conserve energy. And if we don't conserve energy, then the collision must be considered inelastic and not elastic. All right, now we're going to do one practice problem down here, and we are going to assume that this particular situation is elastic. Now, like I said before, it's very, very rare. It only happens with small particles. But just for practice, we're going to assume that it is elastic. All right, so we have a 25 kilogram bumper car moving to the right at 5.5 meters per second that rear ends a 35 kilogram bumper car moving to the right at 2 meters per second. After colliding, the 25 kilogram bumper car has slowed to 1.4 meters per second, still moving to the right. What is the velocity and direction of the 35 kilometer bumper car? All right, so we're going to just assume elastic here. All right, we're going to set up the same organizer that I've been using, mass, initial velocity, final velocity. All right, I'm going to try to be consistent this time. We're going to call this bumper car A, and this one B. Let's see if I can keep that in my math this time. So A, B. So A has a mass of 25 kilograms and is moving initially at 5.5 meters per second to the right. B has a mass of 35 kilograms and is moving to the right, but at 2 meters per second. The bumper car rear ends bumper car B and slows to 1.4 meters per second, although it is still moving to the right, so we leave it as positive. And then the question is, well, then what is the velocity of B? All right. Now, I'm going to do it out one way, and then if I have space, I'm going to do it a different way just so you can see both, but we'll see. All right, so I have the mass of A times the velocity of A plus the mass of B times the velocity of B. So that's the total momentum before, equal to the mass of A times the final velocity of A plus the mass of B times the final velocity of B. And that's the total momentum after. All right, so we plug in numbers. I am going to drop my units here just for space. So 25 kilograms times 5.5 meters per second plus 35 kilograms times 2 meters per second equals 25 kilograms times 1.4 meters per second plus 35 kilograms times my unknown velocity. All right, so I have 137.5, and that's kilograms times meters per second for this first one, 70 kilograms times meters per second for cart B before, for cart A after, 35 kilograms times meters per second plus 35 times my unknown velocity. All right, so now I start combining and isolating, and I end up with 172.5 kilograms times a meter per second equal to 35 times that velocity of bumper cart B. Divide both sides by 35, and I find that the velocity of bumper cart B after the collision is 4.9 meters per second. All right. Now, if I look and ask myself if this is reasonable, it is. All right. The two velocities together after should be similar to the two velocities before. All right. This is the heavier cart, so it gains some velocity, but doesn't get all the way back up to the 5.5. All right. Now, I'm going to go down here. And I'm going to try it with that other formula where the mass of cart A is equal to the velocity of A minus the final velocity of A. And that's equal to the mass of B times the velocity of B final minus the velocity of B initial. And we're going to see if we can get the same answer. All right, so we start with our mass of 25 kilograms. And then for the velocity of A initially, it was 5.5 meters per second minus 1.4 meters per second. That's going to be equal to the mass of B, which is 35 kilograms, times the final velocity of B, which we don't know, minus the initial, which was 2.0 meters per second. All right, so 5.5 minus 1.4 times 25. So we get 102.5 kilograms times meters per second for cart A. Over here we have 35 times our unknown velocity minus 70 kilograms times meters per second. We're going to add 70 to both sides. We end up with 172. Doesn't this seem familiar? Kilograms times meters per second equal to 35 times the velocity of B final. Divide both sides by 35, and we once again end up with a velocity for B after of 4.9 meters per second. All right, so you can see that you can also use this second version of this formula. So it's going to be up to you. You can choose. You just need to make sure that you show the formula that you use. All right, now let's go back up to the rest of the questions here. Which car experiences the greater force during the collision? All right, well, we know the answer to this, hopefully. Neither. They are equal and opposite. All right, so the force at which A applies to B is equal to the force at which B applies to A. All right. Now, if we knew the time of the collision, we could figure that out, but we don't have that piece of information. All right, let's look which occurs greater change in momentum. All right, again, remember that change in momentum is equal to our impulse, and that impulse is equal to the force times time. All right, the time of collision for each object is the same, and the force is the same, which means the change in the momentum is the same. So again, neither. Equal and opposite. All right, which experiences the greater change in velocity. All right, so I'm going to go look at the mass values. Whichever cart has the lower mass should experience the greater change in velocity. All right, and if we look for cart A, 5.5 minus 1.4, that's a change of around 4.1. For B, well, I guess negative 4.1. For B, it's going to be 4.9 minus 2, which is 2.9. So cart A has a greater change in velocity. All right, which makes sense because it is the less mass. All right, now using kinetic energy, show that the velocity of the 35 kilogram cart equals your answer from part A. All right, so because we've decided this is an elastic collision, all right, I know that the kinetic energy before has to equal the kinetic energy after. So another way to figure out a velocity value for an elastic collision is to use the kinetic energy formula. All right, so for that, I would say that 1/2 the mass of A times the velocity of A squared, plus 1/2 times the mass of B times the velocity of B squared has to be equal to 1/2 the mass of A times the velocity of A final squared, plus 1/2 the mass of B times the velocity of B final squared. So those have to be equal to each other. And I know all these numbers except for this velocity value. So I'll do the same thing I did before. I'll plug everything in. So 1/2 of 35 times 2.0 squared plus 1/2 of 25 times 5.5 squared has to equal 1/2 of 25 times 1.4 squared plus 1/2 of 35 times that unknown final velocity squared. So I'm going to need to take a square root at the end. All right, so I'm going to get 70 joules for here. Whoops. 378 joules for cart A. And then I'm going to have 49.5 joules for cart A after, plus 1/2 of 35 is 17.5 times my unknown velocity value squared. All right, so I subtract the 49.5 to the other side, and then I divide by 17.5, and I get 22.8. That's going to be equal to the velocity of B final squared. So I have to take the square root of both sides, and I find that the velocity of B after is around 4.9 meters per second, which is exactly what we found using the conservation of momentum. All right, so you can look at it from either perspective as long as the collision is elastic. If the collision is inelastic, then you can only determine that velocity value by conservation of momentum, because the energy is not conserved if the collision is inelastic. Okay? All right, so if you have any questions, please let me know. If you need to go back and review any of the collision types, please do so. Just do not forget that a total inelastic collision is very different than an inelastic collision. You need to make sure you recognize the difference, and that an elastic collision is different from an inelastic collision. Okay?